All right. So rational functions are really the quotient of two polynomials. Quotient being the result of a division problem. So I take one polynomial and divide it by the other. That is what we define a rational function as. A lot of times you'll see it described as f of x equaling p of x divided by q of x, where p and x and q of x are polynomials. One thing we just did in the warm-up is determine that the denominator cannot equal 0. And that's going to do something to our graph. And that's really what we're working on today and tomorrow, is being able to graph these rational functions. I also have just a couple like basic rational functions or parent rational functions that I do want you to kind of jot down. So 1 over x is probably the most basic rational function. It's also described as the reciprocal function. And so I want you to just kind of jot down that shape. And what I'm adding in here are what's called asymptotes. And we're going to actually talk about how to find those asymptotes here in a second. For the most part, those asymptotes show up anytime we divide by 0. Okay, and then 1 over x squared gives us a little bit different shape. Because of the squaring, we're not getting any negative y values. So that's why this branch kind of over here in 1 over x is flipped upwards. Okay, so it'll always just end up being positive. And I'll give you all a sec to write this all down. I mentioned these asymptotes, and I think for the most part that's a new concept for us. And it's a really big feature of rational graphs, also of other graphs that we'll get to as we move through our curriculum. And here's how they show up. So first, vertical values where we divide by 0. Okay, so when we divide by 0, that's an error in the algebra. And as a graph, it shows up as what's called a discontinuity. Okay, and that discontinuity can either be a vertical asymptote or it can be a hole. So the asymptote creates a unique feature where the graph is going to get really, really close to that asymptote, but it'll never actually intersect at that asymptote. Okay, so I'm going to abbreviate vertical asymptote as VA, just kind of saves us some writing. So from here on out, you'll see vertical asymptote as VA. And to find the vertical asymptotes, we need to factor both the numerator and the denominator, just like what we did when we were simplifying rational expressions. Now, that was a long time ago. Okay, we were simplifying rational expressions back in like early September. And one of the first things we would always do is factor both the numerator and denominator. And we'd look to see if any of those factors divide out, meaning there's the same factor up top and on bottom. When the factors divide out, that actually is what's going to create a hole. Okay, and those values are not vertical asymptotes. Those are actually holes in the graph. I'm not going to really get into kind of how we can see that on the graph. In fact, it's almost impossible to see it until we actually graph these functions. Today, it's more about covering some of these concepts of these rational graphs. Okay, once we factor the numerator and denominator, if there are any factors that do not divide out, then we're going to solve for the zeros, and these are vertical asymptotes. And know that there is not any limit or any rule as to how many vertical asymptotes or holes we could have. We could have infinitely many holes, infinitely many vertical asymptotes. Just because we have one doesn't guarantee another. Each rational function is kind of unique in where the vertical asymptotes and their holes show up. It's also possible for them to have no vertical asymptotes or holes. So we're going to work through a quick example or a few examples. We're going to look at the rational function, and we're going to describe the places that we have vertical asymptotes and their holes. I'll do part A for us. Okay, so again, a good place to start is factor both your numerator and denominator. So for f of x in part A, the numerator of x doesn't factor any further. The denominator, well, that actually showed up in our warm-up, x squared minus 9. We could find the values that make that equal to 0 by setting it equal to 0 and taking square roots. This actually also factors, right? Two numbers that multiply to negative 9 and add to 0 are 3 and negative 3. So this factors to x minus 3 and x plus 3. And that's actually going to be a much better habit for us to get into, is factoring rather than just setting equal to 0 and taking square roots. Mainly because if we have any factors that divide out, we want to catch those. So I'm noticing that there aren't any common factors in the numerator or denominator. And so what I'm going to do next is take each factor in my denominator, set them equal to 0, where I get x equals 3 and x equals negative 3. Now these are values that we are actually excluding from our domain. They're values that make us divide by 0, which is a problem in the algebra. And that's what creates a vertical asymptote. Okay, so these are the equations of both vertical asymptotes for this graph. And again, they're vertical asymptotes because the factors do not divide out anywhere. Had we had like another x minus 3 on top and on bottom and those factors divide out, we would then have had a hole there. Okay, and I'm going to have you all work through B and C, identify any vertical asymptotes or holes that you can find in B and C. You're going to do that on your own after you're done. Check with your group, see what they come up with. All right, okay. Part B, the denominator factors the exact same way into x plus 3, x minus 3, but this time I get those x plus 3s to show up in the numerator and denominator. Those factors divide out. And so this equation g of x simplifies to be 1 over x minus 3. And that's actually what we would see if we were to graph this. If I graphed both the original equation and the simplified equation, it's going to look the exact same. The one difference between the original and the simplified equation is the fact that we get this hole at the value that makes that factor equal to 0. So x plus 3's divide out, and the value that makes x plus 3 equal to 0 is negative 3. So there's going to be a hole at x equals negative 3. And again, we'll talk more about what that looks like on the graph once we actually start graphing these rational functions. Since x minus 3 does not divide out, that means we have a vertical asymptote at that value. Okay, so in this case, there's one hole and one vertical asymptote there. In part C, x squared plus 9, that does not factor, right? There aren't any two numbers that multiply to positive 9 and add to 0. Thus, we would get a non-real number, kind of like what we saw in the, what was that, R of x warm-up problem, where we don't need to exclude the imaginary numbers. We're only excluding the real numbers. So in this case, there is no vertical asymptote and or hole. Questions here before we move on? Okay, we have time for like one last thing, and it is actually kind of relevant to rational graphs. And it is called arrow notation. Now, I don't want you to write this down. I think this is things we can just kind of think our way through. If you're someone that you're like, I need to write it down, I'm going to ask that you actually pull up the notes after we're done with class today in Schoology. We kind of saw this first semester when describing end behavior, to where if we see this notation, we want to understand what is it saying. So the arrow is meaning like as x goes to. So the arrow is almost like goes to or approaches. So this is saying as x goes to the value of a, the sign next to it is telling us which side it's approaching from. So if x approaches a from the positive side, that means that x is approaching a from the right side, right? Positive being on the right. Similarly, if x approaches a from the negative side, that means x approaches a from the left side. So this is a way for us to describe what the graph is doing as we approach certain values. Now, we're not going to do a ton of this in this class. We will with these graphs here. This is a really important thing as you move into pre-calculus and calculus, which that's kind of the end goal for a lot of you. You see this notation all over the place in calculus. Okay, so just starting to get us familiar with that. Then, of course, as x goes to infinity, approaching infinity from the right side, as x goes to negative infinity, same idea. So it's a way for us to describe what the graph is doing as it approaches some of these vertical asymptotes or even holes. This is a good example as to what we're really seeing. And again, I don't want you to write this down because we are going to practice this here in a second. So this is saying as x goes to infinity from the negative side, so the left side, what are we seeing that the graph is doing? Well, as I approach 0 from this left side, I'm noticing that the values are going up very quickly, and thus they are approaching infinity. So this is saying as x goes to 0 from the left side, the function or the y values are going to positive infinity. Same thing on the right side, right? As x approaches 0 from the positive side, we're also seeing that the y values are going to infinity. Okay, so it's kind of another way to describe end behaviors or just kind of features on graphs, especially around the asymptotes. So here's what I do want us to write down, because we're going to just kind of do a quick example of this. So if we have g of x, which I actually have the graph for g of x below it here, we're going to first just find any asymptotes and holes from this graph. So go ahead and write down this equation. And the first thing we're going to do is factor everything, just like we talked about. So the numerator is already factored at x plus 3. The denominator, the only thing I can do in the denominator is take out a common factor of x. So I'm going to factor out an x, where I have x times x minus 3 as its factored form. The first thing I'm noticing is there are no common factors in the numerator and or denominator. So there aren't any holes. So the values that make these factors equal to 0 are going to be vertical asymptotes. So making it 0 and 3, both being vertical asymptotes. And so below here, I actually have the graph for g of x. I do want you to kind of just make a rough sketch of that. And we're going to include the asymptotes in this graph as well. So we have one asymptote at 0, another one at 3. So our graph is ultimately kind of determined based on where these asymptotes lie. And you can see we get a few different branches, one to the left of the asymptotes, one in the middle, and one to the right. And this is a place where we can go ahead and describe or use that arrow notation to describe what the graph is doing at these asymptotes. So this left side here, we're going to say as x goes to the value that it's approaching, which is 0, we're going to also describe the side we're approaching from. So since we're approaching from the left side, that's the negative side of that value. So as x approaches 0 from the left side, the function is increasing, okay, and increasing without bound. So we're going to say that the y values, or f of x, is approaching infinity. So as you get closer and closer to 0, the y values are approaching infinity, okay, going very high up. On the flip side, Or actually, let's just take on the other side of 0, which is below the x-axis. So this is the same x approaching 0, but this time from the positive direction, or the right side. This time I'm noticing that the y values, or f of x, is getting negative, and thus approaching negative infinity. So f of x is approaching negative infinity. And we'll do the same thing at 3. So as x approaches 3, like, okay, which side am I approaching from over here? This is the right side, which is the positive side. The function is going up to positive infinity. And then lastly, as x approaches 3 from the negative side, the function is going down to negative infinity. We are going to actually stop right there for today, as you are out of here in about a minute. Know that the